Okay, there's no numbers, but this is number 1. This is about differential equations. So dy dx, right? This is our general form of our differential equation. Equals something, right? Also known as y prime, also known as f prime. There's lots of ways that we can begin representing a differential equation. Okay, so this one says that we have f prime. Notice this is f prime. Maybe you didn't notice the tiny little f prime, but that's f prime is some equation. Okay, so that's true that the derivative is this. It's 4 times x minus 2 times x times the y value, right? F of x is the y value for that given x. And then we have some initial conditions. F of 0 equals 5, right? That's an initial condition. And the limit as x approaches infinity of our function is 2, right? That's the horizontal asymptote going to the right. The y values approach 2, right? It's good to understand what it is that we're given, some information. And now we're given this. Find the value of the integral from 0 to infinity of our function. Okay, so this is called, in case you don't know, an improper integral. Okay, we never evaluate improper integrals. We first change them, and this is exactly what calculus is going to be looking for. You need to change your improper integral to the limit as some value goes to infinity, and we traditionally call it b, of our integral from 0 to b. So notice we've taken the infinity and written it as a limit. So now we're talking about horizontal asymptotes. That's what the limit as a value goes to infinity is. Of, well, what was the name of this function? Because this function does not look fun to try and anti-derive, does it? But the name of this function was f prime. The name of our function was f prime. So let's, instead of writing all of that stuff, which can be pretty, hard to look at 4x minus 2x f of x and try and anti-derive that, because that's what our integral is asking us to do, is to anti-derive. But at its most basic level, what is the limit, or what is the integral of an antiderivative? Right? Or of a derivative. What is the antiderivative of a derivative?
The normal.
That's just the function. The normal. The antiderivative of a derivative is the function. Right? So we have some function called g. We take its derivative, that's called g prime. Okay? If we have some function g prime and we take its antiderivative, what does it end up at? It ends up at just g. Okay? We're taking the antiderivative of a derivative, which ends up with a function. So this is a fundamental theorem of calculus problem. We are trying to evaluate our function from 0 to b. From 0 to b. Okay, and what does the fundamental theorem of calculus say about that?
It says it equals f of b minus f of 0.
F of b minus f of 0. So the function evaluated at the top value minus the function evaluated at that bottom bound. Right? Those are your limits of integration, your 0 and your b. Well, do we know what f of 0 is? Yeah, f of 0 is what?
0.
F of 0 is 5. It says so in the problem. F of 0 is 5. It says so right there. F of 0 is 5. So now let's actually take the limit like it says to. It says what is the limit of the function evaluated at any value? What is the limit of our function for all values of x? It's 2. The horizontal asymptote for our function, no matter what the x value is 2. Minus, what is the limit of a constant? the constant, right? This is a horizontal line. So, of course, the limit of our constant is a constant. It does not change. It is not variable, right? Variable means change. Constant means the same always. So the answer is 2 minus 5, which is negative 3. Okay, the next part B says use Euler or Euler's method to approximate f of negative 1 starting at x of 0. Okay, so that's our first value, x of 0, with 2 steps of equal size. Okay, so we did this by making a table. The table doesn't earn you any points for calculus. Okay, so here's your steps. We have the 0 or your initial values, and then we have our first step, and then we have our second step, right? These are the amount of steps. And then going down, we're going to have your value. So your first is your x sub n, and then your y sub n, and then our last one is your derivative, right? Evaluated at each of these steps. Okay, this is just a way to organize our information. So going back, our first x value is 0. Okay, our first x value is 0. What's our first y value? When x is 0, y is 5. That was given to us in part, well, the opening to this equation. And then dy dx, well, that is your 4x minus 2x f of x, right? That's y prime. That's f prime, right? All these things have the same different ways to write their names, but they all mean the same thing. So what is 4 times 0, right? That's our x value, minus 2 times 0, times, what is f of x? What is f of 0? Well, f of 0 is 5, but 0 minus 0 times 5 is 0. Okay? So here's what we need to know. Our function evaluated at any step is your previous y value, right? So y sub n minus 1 plus the change in x times the previous derivative. Okay, and there's lots of ways to write this. This could be written as dy dx. Okay, this can be an h in some equations, but it's basically all the same. Your previous y value plus the difference in our x's times your previous slope. So let's figure out what is the difference between our x's. We started at 0 and we want to end at negative 1, right? We want to end at negative 1. So then what is the intermediate step in between here if we're doing equal sizes? That means every step is
Negative
1/2, right? Every step is negative 1/2. So delta x, for every one of these problems, delta x is going to be negative 1/2, right? That's our step size. We're starting at 0, we're going to negative 1, and we're doing 2 steps to get there. Okay, if we did 4 steps, then it would be a quarter. We would be doing a quarter every time, 0.25, 0.5, 0.75 to negative 1. Okay, so that's your delta x, the change in your x values every single step. So first, let's calculate what is our next y value. Okay, so that's f of negative 1/2. Okay, negative 1/2 comes from right here. That's your x value that we're talking about. F of negative 1/2 is approximately, right, so not equal to, but approximately, our previous y value, which was 5, right, that's our starting y value, plus negative 0.5. That is our delta x. That's our change in x. Times what was our previous derivative? That's from down here. Our previous derivative was 0. Right, that was our slope down there. So I guess this just comes out to be 5, doesn't it? So we put a 5 in here because that's our approximation. Okay. Now let's calculate this, our next dy dx. Okay, so that's 4 times something minus 2 times the something times f of that something. What's our x value is?
Negative 0.
-1/2. Okay, so one step at a time. 4 times -1/2 is -2. Okay. Minus a minus is a plus. 2 times 1/2 is 1 times what is f of -1/2?
5.
That was 5 that we just calculated a second ago. So -2 plus 5 is 3. So our last thing, this is what we want. We want to know what is f of -1, right? That's what we want. So we're going to be done after we find f of -1. So our previous y value was 5, right? That's the thing that we calculated right here. Also showed up right here. Plus our delta x doesn't change. It's still -1/2. But what's our new derivative? That's 3, right? That's the value from down here. So now we just have to math this out. 5 plus, or 5 minus, what's 1/2 of 3? I believe that's 1.5, right? Half of 3 is 1.5. 5 minus 1.5 is 3.5. And that is your answer. Okay? So calculus gives you 1 point for figuring out what the second y value is. They give you 1 point for the notation, literally writing it correctly, and then 1 point for the answer. Okay, which is why we always write it f of whatever x value we're talking about. Okay, and now the fun one. Hopefully it's the fun one. But finding a particular solution. So we're going to use all of our algebra, and we're going to find out what y equals. Okay, so we start with our dy dx equals 4x minus 2xy. Okay, done. Now your first step is to separate. No, we don't want to separate our variables first. We can only do separation of variables with multiplication. So we have to factor this guy. What do 4x minus 2xy have in common?
2x.
They have a 2x. So we're going to factor out the 2x from our equation. And that leaves me with 2 minus y, right? Because half of 4, 4 divided by 2 is 2, and then the 2x is gone, so minus y. Now we're going to separate your variables. So we're going to divide both sides by 2 minus y. That's going to come over here. We're going to multiply both sides by dx. That's going to come over here. Okay, we want the x stuff on the right and the y stuff on the left. So my equation looks like dy over 2 minus y equals 2x dx. Which leads us to the integral, right? We haven't done any calculus yet. It's all been algebra. So now we're going to integrate both sides, and this becomes the calculus. Okay, what's the integral of dy over 2 minus y? Natural log of 2 minus y. Natural log is always positive. Your denominator goes into absolute values in case you happen to have a negative thing in there. And what's the antiderivative of 2x? That's just x squared plus c. So now we're going to use our initial condition of f of 0 equals 5. Right? With the initial condition f of 0 equals 5. So negative natural log of 5 minus 2 equals 0 squared plus c. So c is the negative natural log of 3, right? So because 5 minus 2 is positive, we don't have to worry about the absolute value anymore. so now let's come back up here, and we're going to solve this equation for y. So we have negative natural log of y minus 2 equals x squared minus the natural log of 3. C was negative natural log of 3, so it becomes a minus when we plug it in here. Okay, how do we get rid of natural log? Well, let's get rid of the negative first. That would become a positive, and we'll just move everything over here and make all that negative. So natural log of y minus 2 equals natural log of 3 minus x squared. Now let's exponentiate, right? This is how we get rid of the natural log, is by exponentiating. Y minus 2 equals e to the natural log of 3 minus x squared. Okay, next we're going to add 2 to get y by itself. Notice it doesn't actually add to anything. So we can put a 2 plus e to the natural log of 3 minus x squared. Okay, which is probably not how you're going to see this written. So let's simplify that. This is 2 plus e to the negative x squared plus natural log of 3. Right? And our plus is going to change into a times e. Okay, because that's one of our properties of exponents. So most likely you're going to see this written like this. Most likely. Okay, there you go. That's some wonderful stuff. And that's the first page of this differential equation and logistic thing. Okay, check back for more pages soon.
So